Thanks, Paul. Thanks, IoT Security Foundation for inviting me. It's a privilege to be here. I'm an academic, so I will talk about a problem that you working in the real world are going to solve. So today, the problem is talking about security by design in the context of IoT. And for that, I use CrossCon, this project which I'm involved. And CrossCon is relevant because it focuses on the problem of designing and implementing the root of trust in IoT, in edge devices. As you know, the root of trust is important because in order to build a secure system, essentially cannot be done without having a component that is assumed to be trusted to work correctly, trusted to be secure, and you cannot verify. And then you run really the software that the security critical function. Once you have that component, then you can build security as complex as you want, and you can also verify those security that is built on top of it. Since we need to trust it, and then it's also smart to keep it small and simple, because then we have a higher chance to make it right. Now, in the context of CrossCon, we look at devices that are edge device, mainly MCUs. And there we cannot afford, in many cases, we cannot afford to have an extra chip to implement the root of trust. So there, the root of trust is implemented through this concept of the trust execution environment. You find there the definition. So on the main chip, you have the main chip operate in order to create an isolated execution environment where you can run the trusted code. Okay, and that is the T. And most of the MCU and most of the chip manufacturers implement this TE. Now, the problem is there are still some open issues on the current technology of implementing the TE, and that I want to discuss about a couple of them. Now, this is more or less, you find there a lot of the technology that are in place. Nowadays. It's not important to see the details there. We added also the one on the open hardware specification, RISC-V, because there is a couple of proposals. And on trust zone, you might have a lot of companies like Qualcomm, Huawei, that have their own T, but essentially using the NXP, but using the trust zone technology. Now, what is important in this picture to notice is that the T is the gray boxes are the T and what run in it. And what is that you can easily see is that they have different shape. The different shape reflect the fact that they are built using different trust model, and that it's a bit of a problem because you have some T that assume to have a trusted OS, some not. Some trust the user, some other not. Some use an hypervisor, some not. And that it's a problem if you need to develop an application running on the T, because you need to know on which platform your application is going to run. And because depending on the trust model, you have to develop differently your security application. And that it's less than an ideal situation because essentially we have a serious interoperability issue because you need the same to develop the same application in different way depending on what is the trust model on which is going to run. While you like once you choose a trust model to develop the application once and run no matter in what hardware then is going to be. This also raises the cost of adopting this technology, a cost that it's already high because this is really closed technology, so it's not easy to put some trusted code inside the TE. So interoperability is an open issue with the current technology. Then we have portability issue as well, and particularly in the two ends of the spectrum. So when you talk about IoT, there are billions of devices that are already deployed, and these are bare metal. Bare metal are all these devices for which it's too complex to implement a TE, and they are simply uncovered by any security. Usually those devices do not do processing of security critical function, it's okay, but they often provide input for other components that do security critical function. And we know, we have a lot of examples of how attacker can compromise a system once they know to and can control the input to this system. And then more and more, also in the edge device, we see not only a CPU, but we see a GPU, some AI-specific processor like NPU, TPU, and we don't have to forget about reconfigurable hardware. For this type of processor, there is almost no solution about TE, so they are uncovered, and that it's a problem. Then there are some interesting new requirements emerging from hardware platform in some domains, in particular automotive. Nowadays, they talk a lot about mixed criticality architecture. It's an interesting concept, and it's also, from the economic point of view, appealing, because you have all this industry that spend a lot of money on certifying an hardware. And once you have the hardware certified, you like to use it at the most possible way, so to have different applications running on the same hardware. Because if you have a dedicated hardware per application, you need to certify a lot of hardware, raising the cost. Now, the things works fine. The problem is when you need to mix some safety critical and non-safety critical application, because there to run this, in this context, the safety critical application in secure way, there is no real support of the TE for doing something like that. So these are open problem, and with the Crosscon, I put there some idea that are close to be adopted, to be ready to be transferred in the market, but there are ideas that we think are interesting and not far from be ready. And we have proposed this security IoT stack, and that rely on hypervisor that run on the hardware. Now, of course, to make sense, we need to accommodate all the existing technology there. So the hypervisor use all the virtualization features that the hardware provides you. It can be RISC, ARM, or other architecture. And on top of that, if there is an existing TE, it will run the existing TE inside the virtual machine to isolate that TE. If there is no TE, then you create a virtual machine and emulate the trust model of the missing TE. And this allows you to run on the same hardware different TE. So you can have, like in this case, the same hardware application that can run, that need SGX or trust zone on the same platform. If you have an Intel platform and then you have SGX, you use the real SGX, while the trust zone is emulated through software. Then we also complete with, for architecture that do not have a TE, we implemented one, in particular for RISC-V, and also we have a solution for the bare metal I told you. A software-based TE that can run on very limited device. And we have also a solution that can fix the problem of the mixed criticality architecture. Now, we have this, and as I said, there is a lot of software there. So when we develop this software, and in general, when company develop this trusted firmware, is there enough assurance? Because remember, this is supposed to be trusted by definition, secure by design. And here, let me tell you a few words about this the problem of assurance. Now, look at this. This is the case of the trust zone. And here we have a sort of bad news. And this is not only for trust zone, but for the TE in general. Because you can see already in the gray area, there is a trust OS running. There are thousands of lines of code already in the TE that, as I said, are supposed to be correct. And the trend is to put even more code inside the TE, because soon there will be an hypervisor. And once you have an hypervisor, the temptation to have not a OS, but two OS, it's very high. So there we have a problem that these are getting too complex. Too complex not to make mistakes, not to have vulnerability. And added to this, then it's a negative trend, there is the issue that even existing TE don't seem to have the level of assurance that we expect from software that need to be secure by design, because these are a list of vulnerabilities that have been reported. And again, I put trust zone, but this problem is across any TE technology. And some of these are architectural vulnerability, so depend on the TE, but some are really software vulnerability that we already knew and simply are there because of the sloppy implementation. That it's a signal and evidence that essentially in the tool chain they use, there is not enough attention, they don't pay enough attention to the security issue, to the correctness issue. Just to make a concrete example of what you can do to push assurance in the tool chain, I tell you the specific case of CrossCon, where there what we are completing is a secure cross compiler for C, since most of this firmware is written in C still. We know that C is unsafe language. As mentioned today, still 70% of the vulnerability relate to unsafe code. So at least there we have the compiler by design producing safe code. Also, at the linker level, you can do stuff, because most of the time you have this firmware that it's a bundle that include always some binary provided by third parties, and you don't have the source, so it's difficult to say how secure is this binary. One option is fuzzing, but it's very resource consuming. It takes a lot of time to do fuzzing and a lot of resources. Here we develop a tool based on AI that, for example, has with a good accuracy detect non-vulnerability directly with the binaries. So this is a sort of level of assurance that you can add. The same is at the loader level. When you load the software on the device, you make sure that all the configuration files are correct, that you partition the memory in a correct way. And then and as I said, we have a cross compiling, so then we have object code that can run. At the moment, we just support ARM and the RISC-V. And let me finish with something that we saw several times today, that is the IoT firmware update, in particular the IoT trusted firmware update. There the solution is far from being satisfactory, and many times this morning people mention about CRA. If you read the CRA, half of it is about firmware updates that are particularly important, since some of these systems are not only security critical, but are also safety critical systems. Now, the solution there, the trend at least is in the right direction, because 5-6 years ago, no firmware or very few firmware was updatable from remote. Simply by design, the firmware could not be updated. Still, today, most of the trusted firmware cannot be updated. But people are realizing, chip vendors, device vendors are realizing that there is a lot of line of code in this device, and you cannot ship software without supporting update. And now most company, a lot of company actually are implementing and are accommodating the protocol for firmware update. The problem is that the situation is too fragmented, because each company tends to have its own proprietary solution to do the update. or having industry-level update. And that it's a mess, because usually on this device, I have components coming from different vendors. And if each component adopt different methodology, different policy for the update, at system level, I have no clue what is going to be in the device, and that it's a problem. There we need a standard way to do it. A standard that, in order to succeed, need to be flexible and extensible. Flexible, extensible in order to accommodate what is already there. And in case, again, of Crosscon, we had a look at this suite. It's a software update for Internet of Things. There is an IETF working group there. They issue already some RFC, but it's not an RFC yet. This is interesting because it's flexible and extensible in the same way. Together with the classical image of the update signed, there are metadata in this manifest. And this manifest, essentially, you can put extension. Extension like, for example, the one of that link to the bill of material. And what it's also something interesting to observe is that many times we mention about the bill of materials today. And the bill of materials and the secure update mechanism are completely in isolation. They work in isolation. There is no operational link between the two. Okay, and that is a sort of missing bit, because there is a lot of information that when I do the update, I can use, and it's interesting to have from this BOM or from other scheme that already exist or soon will appear, because there is a lot of work on this national device certification scheme across Europe, and it's likely that you need that information in the update. Then let me finish saying, when we want to do the update, I think we can do a bit better than the usual update, where we just check for the integrity and the authentication, okay? And here I think security should learn a bit more from safety people. So there in the manifest, what we can add is also some certification about the behavior, the security behavior of the update. So when I have an update that introduces a functionality, I want to know also what are the security consequences of that functionality, because then I might decide not to update, because from the security point of view, I have a problem. So that it's a lot of work that needs to be done, and as I say, that at least the direction is there, and CRI will push things because making them mandatory. Okay, so if you want to know more about what I said, that is the link to the project, and most of the things I said are under development. Some are already developed, and it's almost all open source, so feel free to visit the GitHub, use it, and then if you have any question, please contact me. Of course, I'm just the front end of many people that work on the project. Thank you.